Okay. In the previous video, we went through this plausibility argument from several perspectives, right? To show that nuclear fusion inside a star like the sun can supply enough energy to power, the luminosity of the sun over its lifetime, and that the idea of quantum tunneling or the de Broglie wavelength being the distance of closest approach that you need to reach um, actually is consistent with what we know to be the temperatures at the core of the sun. The other bit of sort of mathematics that needs to go into this is to figure out how fast the reactions happen. Right? When we talked about the transitions between bound levels in an atom, we talked about these A, B, and C rates, and the total rate on the right-hand side of those equations was often in units of number of events happening per unit volume per unit time. That's sort of the same thing that we want to talk about for nuclear reaction rates. So for example, if we have a nuclear reaction that takes, species N1 and collides it together with species N2 and creates a new species N3. The reaction rate for that is often written as R12, 3, just to show that it's 1 and 2 going into 3. And again, it's the same sort of units, number per unit volume per unit time. And this R ends up being like it was before for atoms. It's the right-hand side in the equation that tells you how does the number density change as a function of time. So, right, so if we've got this N1 plus N2 going into N3, then there's three equations we have to worry about: the number density for species 1, the number density for species 2, and for species 3. Because this is a reaction where species 1 and species 2 are disappearing and creating a new species 3, the rates for species 1 and 2 are going to be negative, minus R, and species 3 is being created, so that's a positive thing, right? In every reaction, we lose some N1s and N2s, and we gain some N3s. And there's a general way of looking at this. What I showed up above was just sort of an idealized system where there's only this one reaction going on. In reality, say in the cores of stars, there's millions of reactions happening all the time. So if you really want to figure out how is this one species changing, you've got to sum over all of them, right? So this first term shows you how you sum over all of the ones with, if we're following species I, we have to look for all the reactions where I is one of the ingredients, and we sum over all of the other J's that it can interact with, and that's going to get a negative sign out front because the I's are disappearing in these types of reactions. But then we also have to look at all the reactions where I can be one of the products. And then we have to sum over all the other ingredients that can give you I as a product, and that's going to be positive. So that's just the general thing to do in a situation like this. So for example, in the sun, if we simplify the whole thing into one hypothetical single reaction where 4 protons come together simultaneously to turn into helium, the equations are going to look like this, right? The rate of growth of the helium is going to be, if that's plus R, then the rate of loss of the number density of protons has to be minus 4 times R, because for every one helium that gets created, you're losing 4 protons. Yeah, I don't know how important this is, but if we then go back to the language that we defined when we talked about mixtures of different elements, right? X is the mass fraction of hydrogen, Y is the mass fraction of helium. These are those same definitions that we used before. We can convert these two equations into a single evolution equation that shows you, say if the mass fraction of hydrogen is going down, the left-hand side here is going to be negative, and that means that the right-hand side has to be negative, which means that this dy dt, which is the rate of change of helium, has to be positive, right? As we lose hydrogen, we gain helium. So there's just different ways of writing these rate equations. How do we determine the reaction rate? Well, we know that it has to depend on a bunch of things. we know that the reaction rate ought to depend sort of linearly on the product of N1 and N2, right? If there's twice as many particles of species 1 hanging around in this region where fusion is happening, there's going to be twice as many reactions. There's twice as many particles of type 2, there's going to be twice as many reactions. And if you double both of them, there's going to be 4 times as many reactions. We also realized that this should also depend, at least linearly, on the relative speed between the 2 particles. Because if we're counting up reactions that are happening, and this v is the relative speed between particle 1 and particle 2, and we just look at one particle and watch the other ones stream by. If the relative speed is 2 times bigger, then over a given time, 2 times as many particles are going to stream by, and you're going to have 2 times as many reactions. Again, this is a per unit time type of a quantity. So when you put those together, the N1 and N2 and the V, to get the units of an R, the only other thing that has to be here is this sigma, which we call a cross-section. It's got units of an area. So we can think of it like a cross-sectional area, right? This little cartoon over here shows that, if you've got a particle coming in to a given target particle and it's within this cylinder here, right? If it's going to hit this cross-sectional area circle here, then there will be a reaction. If it's outside that area, it's a miss. There's not going to be a reaction. Again, that's a very sort of if-then way of thinking about it. Quantum mechanics is fuzzier than that, but it's still a quantity with units that needs to get computed. There's maybe 2 or 3 other lectures worth of derivations if I wanted to go through how does this get computed as a function of, say, the temperature and the density of the material in the center of a star. You have to average over Maxwellians. You have to take into account this idea of quantum mechanical tunneling and the de Broglie wavelengths to compute the size of that cross-section. I think I'll try to find a good video or another place you can read about that derivation. I'll put in the description, and you might see more about it in future astro courses, in the upper level courses. But for now, I think I'll just skip to the end of that calculation. Usually what astronomers tend to find, we like to fit power laws to things. So typically we find that these rates are proportional to the square of the density, which is really that same square of the density there, times the temperature to some positive power that we call n. And it's kind of interesting. It's rare to see powers of things in physics and astronomy where the power gets up to double digits, but here it sometimes does. For the current sun, that power is something like 4, but if you look at more massive stars that might go supernova, you can see powers as big as 20, which is kind of freaky to see. But that tells you that if you change the temperature just a little bit, you'll change the reaction rate by a huge amount. So that's the rate. How often do the fusion reactions happen? The more useful quantity to compute is usually something that we call an energy generation rate. If we want to know how does the luminosity of a star get created, we want to know how much actual power in terms of watts do the fusion reactions create. So rather than talking about number of events happening per unit volume, per unit time, what astronomers do is convert the rate into this energy generation rate, which is in units of watts of power, joules per second, per kilogram of material in the core of the star. So you can verify that just multiplying the rate by the binding energy per reaction gives you, takes you from number of events to energy per event. And then dividing by the mass density takes you from the per unit volume to a per unit mass type of a thing. So if you ever go on to study energy generation in stars, you're going to see a lot of equations that look like this, where the energy generation rate is proportional to 1 power of the density times temperature to some steep power n. And I think we will leave things off there and then move on and talk about what actual reactions are happening inside stars. We were very hypothetical here, right? If you go back here, there's this hypothetical single reaction where four protons come together simultaneously. That's not what really happens. And we'll talk next time about what we think really is going on.